So up until now, we've been talking about the same situation multiple times, where we have a generator and there's a resulting source that comes from it. So let's just call this the generator resistance. This is VG, and then we say everything. One of the things that we've been saying most of the time, or I should say most of the time to be very specific, is that the transmission line is uncharged at t equals 0, and then before t equals 0, and then at t equals 0 we then move this switch down, and then the voltage generator creates a DC signal, the voltage wave that goes forward, and then in the case of if there's a mismatch, then we'll just call this RL, then there's going to be a reflection, and it's going to go back and forth and back and forth. But the key thing that we've kind of implied up until now is that this transmission line, this whole circuit here on the right-hand side, is uncharged up until t equals 0. And by uncharged, that means that for each little segment, when we have our little equivalent series inductor and shunt capacitor, that these are all completely discharged. So then we close the switch, and then eventually the system reaches a steady state. And that's kind of been the main situation that we've talked about so far. But what if, once the system has reached a steady state, that there's a change in the circuitry? So, for example, if you were to do a pulse, this switch would close, a signal would go in, but then when you want to turn the pulse off, you would then flip the switch to ground to bring the voltage back down to 0. So there would be a perturbation. So how do we model how that change propagates through the line to reach its new equilibrium? That's the goal of this chapter. So in this case, there are two approaches that we'll talk about. One is the Thevenin Equivalent approach, and the other is the reflection coefficient approach. So the Thevenin Equivalent circuit analysis, and the other technique that we'll talk about is the reflection coefficient analysis. So the main purpose of this chapter is you want to be able to use both of these approaches to calculate what a new wave is as a result of a perturbation. And then once you figure out what that new wave is, you can use all the knowledge that you've accumulated up until now to figure out how that wave propagates through the transmission line system. So let's just start out with this Thevenin equivalent circuit analysis, and the reflection coefficient analysis will be a separate skill. Now in this case, I'm just going to focus on the general procedure. I'll try to make it as general and widely applicable as possible, but that also means that we're going to have a lot of symbols. And so probably the best way to learn from this is to look at a few examples. So in this chapter in particular, I encourage you to follow with me through the initial procedures, go through these initial steps, but then definitely take some time to look through the examples that we have and use that to try to understand how these processes are put into action. Now for both of these approaches, we'll use the same example. So in this case, we start out with a switch that is shut this way at t equals 0. So that is shut this way up until t equals 0. So from minus infinity up until now, it's our standard circuit that has reached steady state. But now, when t equals 0, we're going to change. We'll call this RG2. This we'll call RG1. And at t equals 0, we're going to move the switch down this way. And so this removes the generator, and also you have this other impedance here that is not the same as RG1. And so the reflection coefficient here changes, the source gets taken away. So the situation changes, and for the system to equilibrate, what that ends up manifesting is another wave that ends up going that way. And so I'm going to call the voltage over here Vj. Now, note that Vj, or V junction, is the same as, in this case, it's equal to Vn. But I'm calling it Vj so that I can generalize it, because this can also happen on the load side, in which case Vj would be equal to Vl. But in this case, Vj is referring to Vn. And so we're going to have this in complete equilibrium, and then at t equals 0, we're going to flip the switch. So actually, to be precise, we'll just call it t equals 0. Now the first two steps for both the Thevenin Equivalent Analysis and the reflection coefficient analysis are the same. So I'm gonna write the first two steps, and just also know that these two steps will also be identical in the next skill where we look at the reflection coefficient approach. So step 1, the main goal is to find V steady state and I steady state. And you can find this by just simply forgetting everything you learned right now and ignore the transmission line and solve for the steady state solution. So at steady state, so this is, you basically ignore the T line. Yay, that's easy. So if we ignore the transmission line, we have ZG1, and then this goes to our load. So then you can calculate our steady state voltage as just being the voltage divider of these two resistors. So I have VG ZL over Z01 plus ZL ZG1. So that step's easy. Next up, we also find gamma G at t less than 0 and gamma L of t less than 0. So we want to find the reflection coefficient back before we flip the switch. So before we flip the switch, it's just the generator. You have ZG1 going into the transmission line, and they have ZL. So our standard situation, but with an extra 1 on the ZG. So our reflection coefficients is, in this case, it's just going to be new minus old. So ZG1 minus Z0 over ZG1 plus Z0. And then in this case, it's the same thing that you're used to. So Z load minus Z0 over Z load plus Z0. So the first thing is to find these 4 quantities, which so far you should have down pat. Shouldn't be too bad. Okay, step 2 is we also want to figure out what the steady state is when it's decomposed into a positive traveling wave component and a negative traveling wave component. So I'm going to introduce this concept here, V steady state in this direction, and also V steady state in the negative direction. So this steady state voltage that we see going across, you can actually decompose it into a steady state positive going wave and a steady state negative going wave. And positive negative is referring to the Z direction. So right going wave versus left going wave. And we can find that by solving a system of 2 equations and 2 unknowns. So the 2 facts that we know is that the 2 added together should be our steady state solution. So VSS plus VSS minus is going to be equal to VSS. And then the second thing is that the currents added together is going to be ISS. So the positive going current is VSS divided by Z0, and the negative going current is VSS divided by Z0 as well, right? And what do we do here? That's right. Don't forget, you have to divide by negative Z0 instead of Z0 if it's a voltage that's going in the negative Z direction. So that gives us ISS. So this gives us a system of 2 equations and 2 unknowns. We can rewrite another way that will be a little bit more in the form of how we want it. So VSS plus plus VSS minus is going to be equal to VSS. And then VSS plus minus VSS minus is going to be equal to ISS times Z naught. So the sum is going to be VSS, and the difference is going to be ISS times Z naught. So this will be a handy equation that we'll use later. Now, since this is where the Thevenin circuit analysis approach deviates from the reflection coefficient approach, I think it's a good time to highlight what the difference between these two approaches are. So the end goal is to figure out what new wave ends up going that way into the circuit as a result of whatever change is happening over here. The Thevenin circuit analysis does so by looking at the change in the voltage at this junction. So the Thevenin circuit analysis looks at the change of this, change at Vj between t equals 0 plus and t equals 0 minus, and the difference is going to be the wave that goes in. In contrast, the reflection coefficient analysis is going to look at the change in the VSS that's going into the line, or what I will later refer to as VSS smiley face. So in that case, I'm referring to, in the case of if it's in the generator side, the VSS going into the transmission line is VSS plus. Okay, because plus is going into the transmission line and minus is going out of the transmission line. So on the generator side, it's looking at the change in VSS plus before and after you flip the switch. Or on the load side, you're looking at the change in VSS minus when you flip the switch. So if the change is happening on the load side, you're doing these same calculations to start out, but you're looking at the change in VSS as opposed to the change in the voltage at this junction. To clarify, VSS negative. And then again, over here, you're looking at the change in VSS positive. So we'll revisit that when we go into the reflection coefficient analysis. But in the meantime, just know that where we're going at is we are going to focus on what the voltage is at the junction before and after the switch flips. And then we're going to use that difference is going to reach an equilibrium by having the system is going to reach an equilibrium by having the difference be a wave that it spits out and shoots into the transmission line. And once you figure out what that value is, it bounces back and forth and you work your way across. So the next step is you draw a Thevenin equivalent circuit for what the transmission looks like at t equals 0 plus. For t equals 0 plus, considering the outgoing wave. So by outgoing, what I mean is if we're on the generator wave side, the outgoing wave is going to be V minus, the wave coming out of the transmission line. If we're on the load end, then the outgoing wave would be V plus. So again, the direction that's coming out of the transmission line. So in this case, at t equals 0 plus, this circuit is flipped over. So we just have this RG2 impedance connected to ground, and that's connected to the transmission line. And so the transmission line, the Thevenin equivalent of the transmission line, is an impedance Z naught here, and then you have a source. The value of the source is equal to 2V minus. So now, step 4 is you have this Thevenin equivalent, you solve for the voltage at the junction at t equals 0 plus. So you solve for Vj at t equals 0 plus. And then once you have that, you have Vj of t equals 0 plus. And you also have Vj at t equals 0 minus. In this case, that's VSS, right? So in this case, VSS is also equal to Vj at t equals 0 minus. As you can see, this voltage here is simply going to be equal to VSS, which we found up here. So once you have this Vjt plus, the difference is going to be the new wave that's sent into the transmission line. So the new wave is going to be equal to, so Vt equals 0 plus new wave. So this is the new wave that's going to go into the transmission line, is going to be the difference is going to be the difference of the junction voltage between t equals 0 plus and the junction at t equals 0 minus, which is, as I mentioned, this is equal to VSS. So the new wave is going to be equal to Vj t equals 0 plus, which again you found in the Thevenin equivalent circuit analysis, minus VSS. So that gives you the new wave that comes across. And then step 6, find the new gammas and propagate the wave. So once you have this, the value of the new wave, you also notice the reflection coefficient changes. So you want to find what the new reflection coefficient is after the switch closes. And then you have the reflection coefficients, you have a new wave, and then it's a new beginning, so you can draw a new bounce diagram. And again, this is best learned through example. So I encourage you to go through the lecture for the other technique, the reflection coefficient based approach, and then work through the examples, and hopefully by the end of that, you should have a basic understanding of how to apply both of these concepts for charge transmission, for initially charged transmission lines.